All right. Good day, good evening, ladies and gentlemen. Um, we're back for another class. Today we'll be continuing with error handling and debugging and agentic AI. Um, on Tuesday, we looked at primarily at error handling, where we talked about retries and callbacks. So is it can any of us would any of us try to give us a recap of what we discussed in Tuesday's class? Yes, Kenneth, please go ahead.
Can you hear me, guys? Can you hear me? If not, then I will try.
I can't really hear you, Kenneth. It's
Yeah, you can. It's
I think Kenneth has dropped off probably because of network. No, he's still here. Um, would anyone else like to try and give us the recap? No
Can I
one?
try there?
Please go ahead, sir.
Let me send something to the group actually.
Okay, that's fine.
Yes, sir. Okay, so that day you started us with what was titled reality of LLM based applications, and the first thing you mentioned is the non-determinism nature of LLM outputs because they are based on probability and in other words, one cannot be certain. I mean about what output it would or it could give. And then you mentioned that failures are normal, cannot escape it, they are inevitable, and that there are different impacts that failures can create. Might be on the UX, that's the experience by the user, quality of service being degraded, and then by impact on costs and being a waste. And then if such persists, then the consumers or the people that use the services will lose trust because they will think the system is not reliable. So you went further to give us reasons why LLMs fail, the chains rather, the LLM chains, why they fail, what predisposes them to failure, and you categorize them into into two, being transient and persistent issues. Under transient, that is transient means something that is temporary, just passing by the way, not something that is steady or just some random unexpected thing that. And the first one there is network failure, and I believe that means because LLMs depend on different routing of networks. So if there's any failure in network, definitely it would impact on the quality of service or the service delivery, so to say. And also you mentioned API rate limits, and I believe this will mean that maybe the number of tokens being injected, rather not injected now, being passed or being processed is beyond a particular limit that has been set. So that can bring a temporary seizure or stoppage to a service, which of course should be retried after a while. And then service established. The second category you mentioned told us was persistent issues, which could be bad prompts. That is, if a prompt is badly engineered, then it could lead to issues. And then token limits. I think this also has to do with the rate limits. I believe they are linked together because maybe if the limits are consistently not put to check, then it can be a persistent issue arising from transit issue. Then budget constraints. I believe this may mean maybe cloud services, if they are, well, I'm not very sure about it, but I think maybe cloud services, the budget, that's the cost per thousand, how they are charged. So maybe if resources are scarce, then it might impact on the service. And you give us reasons, I mean, the method of handling those transient issues. In the case of network failures and the likes, retry is the solution. And remember, you also mentioned that the retry should be done in exponential order. That is, if there's a failure that happens, it should be tried after 1 second, 2 seconds, as the order of one, two, and the likes. And then you went further to tell us that um, it should not be immediate to retry it, or it should be a little pause before, which amount to that scale of time. That's the little I can say now, sir, about the summary of the class, sir. Thank you, sir.
Okay, that's quite a good one. I think I'd just like to clarify that when I mentioned rate limits as under
That's it.
transient issues, the rate limit is not just about token. If you check the limits for the free tier on Grok, you'll see tokens per minute, you'll see requests per minute, you see per day, and I think per month, different limits. It's not just about the tokens, it's also about the number of requests and so on. And when I mentioned token limits under the
Persistent.
uh, the persistent issues, I was at the token limit. I was actually referring to the token window of the model. That one is baked into the model. It's
Context window,
different
sir.
from the context window. It's in tokens.
Okay.
So it has baked into the model, different from the service limits that the provider enforces, which could be
That's it.
with respect to tokens, with respect to requests, and so on. So those are distinct.
What about
Another,
budget, sir?
yeah, budget. I mean, if you're using a paid service, they charge per tokens typically. Yeah, it could be per thousand, per million tokens, as the case may be. But there's a cost. So if you exceed what, depending on the billing method, well, that at some point you could exceed what you have paid for. If it's a postpaid, if it's a prepaid service, then when you exceed what your um service tier, the limits for your service tier, definitely it's going to there'll be
Connect.
failure. Also, for some applications, you manage costs by when you trigger some um what's the term, um
Service.
a certain cost level. When you trigger some cost thresholds, maybe you could set up your infrastructure in such a way that when you trigger a certain threshold, you scale down to a lower cost service. Just try to keep within budget. And if that's the case, then when you now switch over to the lower cost service, it's also likely that that lower cost service will have lower service limits, in which case the likelihood of failure also becomes higher. Um, we looked at we also looked at the major oh no, we didn't look at that. We looked at example code for implementing retries and for implementing fallbacks. We had example code, and I had asked that each person tries to play around with that code, make modifications to it, and see how that works. I hope we did that. One thing we didn't get to talk about was it's yes, we talked about retries and we talked about fallbacks as ways of handling errors in your LLM application, handling failures. But you can also combine both, right? And that's what we will start with today. Combining retries and fallbacks. It's actually the best practice for building resilient applications for you to combine retries with fallbacks, right? And a typical hierarchy of applying this combination is, for example, you attempt using your primary component, let's say GPT OSS 120p on Grok, and it fails, right? If you experience a transient error, then you trigger your retry logic, which could probably be you implement exponential backoff and you retry using that primary component again so for a specified number of times, depending on your logic. And if it still fails after the specified maximum number of retries, then you trigger your fallback. And your fallback would be, let's say, a locally run model on OLAMA, maybe Llama 3.2, 3B, maybe Llama 3.3, or whichever model. And if that still fails, then you have a fallback. You raise an error typically. You could also apply a hard-coded fallback for this final failure. I mean, if your retry did not solve the issue, your fallbacks, you could actually have multiple fallbacks. It doesn't have to be a single fallback. All your fallbacks fail, then you raise an error. In which case, I mean, you've made best effort and it still fails. Then you should raise an error so that you are saying something.
No, sir. Apologies, sir.
Okay, no problem. So that's typically how you would combine retries and fallbacks to make your application more resilient. Any questions so far? Any question or comment?
So does that mean that there would be a link between knowing if those retries have failed and to trigger fallback? There'll be a link or a
A
chain
link in
between
what way?
I mean,
When you
if the
use an LLM with retry, right? Automatically it handles the retries. If the first attempt fails, it automatically performs the retry. It keeps performing retries depending on your settings. And when it has exhausted the retries based on your configuration of that LLM, it means it has failed. And so if you trigger that same LLM or the chain or whatever the case may be, if you also configure it to have fallbacks, I mean, once the primary component fails, automatically, I mean, the LangChain framework handles this But once the primary one fails automatically, so in this case, your retry will be on the primary component. First attempt fails, automatically launching retries and keeps retrying until it exhausts all the retries based on your configuration. And once it has exhausted all the retries, it means that the primary component has failed. Then automatically it switches to the fallback that you configured. So, but you have to configure all this when you are defining your model or chain, as the case may be. So by the time it has gone through your fallback list, trying to make use of the fallback components you provided, and they all failed, it's going to raise an exception. So you now need to catch that exception and handle it, probably by logging and then raising an exception that can now be caught and handled further up the stack. Does that address your question?
Yes, sir.
Okay. All right. Does anyone else have any question or comment before we move on to you? Okay, no question. So go ahead. Now, we are going to look at observability and debugging. LLMs are typically like black boxes. Generally, most machine learning models are like black boxes, even though some architectures are more explainable. Machine learning explainability is actually a whole discussion on its own. So essentially, a large language model is just a mapping between some input token, well, a non-deterministic mapping between some input tokens and the corresponding output tokens. So you just feed it some input tokens and it gives you some output tokens. You don't really know, you don't really get to see exactly what's happening inside the model. So it's like a black box. So the black box problem is that the logic of the LLMs are, or agents as the case may be, the logic is typically opaque, particularly because of the LLM. Agents tend to be could be complex depending on the workflow that they are trying to implement. And then there could be hidden states, which relates to that being like a black box. You don't really get to see the internal state of the LLM. And I mean, without having an insight into what is happening inside your application, inside your chains, inside your agents, inside your LLM, you encounter challenges like debugging dead ends, as in where you have inadequate information to debug. You can't really find out what's the origin of a bug, what caused the bug, because you don't have much insight into what's happening in your application. You also encounter the risk of cost overruns. If you don't really know what's happening, you could be there, and before you know, the LLM is running and making multiple calls, maybe necessary or unnecessary, and you could be left with a huge bill. You could have used up most of your credits available with the particular provider. I mean, that could sum up to quite a tidy sum. And there's also the issue of lowered trust and compliance. I mean, if you don't know what's happening inside, if you can't explain what's happening inside, you can't really say for sure. And users can't really be sure that your application is secure And that might also have, most likely also have impacts on your compliance, depending on the industrial sector in which you operate. And so it's important to have insights into what's happening in your application, what your LLM is doing, and so on, which is how we avoid these challenges that I describe here as the cost of flying blind. And so you need observability, preferably deep observability. And observability is not just about logging errors. It goes beyond logging errors. It entails understanding the internal state of the system based on its external outputs. And that, like tracing this something called traces. And the three core pillars of observability are metrics, logs, and traces. Metrics are like measurable. They are measures of, usually time series measures of a system's behavior and events in a system. So they're a way of tracking the performance of the system. While logs capture timestamped details, they are like a capture or timestamp details of events and transactions within that system. Traces, on the other hand, a trace, it follows a particular transaction operation through the system. So with traces, you can determine, or you can observe, you can have insights into the specific components that handle that transaction, the path through the system in which that transaction moves. And so that enables you to better understand the internal state and of your system and how that internal state changes. So for observability, metrics, logs, and traces are very important. Any question before we continue? Generally, for any application you're building, observability is important, especially if it's a production application. But what makes it quite important for LLM-based application is because of the fact that LLMs are essentially black boxes. So observability helps to provide a lens into that black box, provides a window for you to look into that black box and get to understand better what's happening inside it. Okay, Kenneth has asked in the chat, he says, so retries and fallbacks have to be included at all costs because of the likelihood of failure. No, they don't have to be included at all costs. You need to do a cost-benefit analysis. What's the cost of implementing retries and fallbacks? And what's the cost of failure? If the cost of failure is minimal, if the cost of failure outweighs the cost of implementing strategies to handle failure, then you may not bother to try to handle that failure. But the truth is that if it's a production system, you most likely than not, you should handle failure. We tried and fallback are two ways to handle failure, depending on whether the failure is transient or it is more persistent. Yeah, Lara, what you please go ahead. Raise your hand.
Yes, sir. As you're speaking about Kenneth's question, something just came to my mind, sir. Before now I've read about something they call streaming and batch processing. In inference, that's when there is a service is being used, such that maybe if a request is needed immediately, that means they call it streaming. And maybe something that can wait, they call it batch. Maybe it can, but I don't know how deeply it may wait. But my question now is, does that, I mean, would that not be impacted by the need or no need for having retries? Like you mentioned now that since it may not be compulsory to always have it due to, I mean, depending on the benefits and costs analysis of the project. So if something is, I mean, does being, I don't maybe don't remember by being streaming and batch, maybe it applies in this case, and maybe that can also determine if retry should be done or not, or with fallback or no fallback. I don't know,
Well,
maybe I'm clear.
batch processing is typically more efficient. Um, you gather the batch of, in this case, inputs to the process, so that you make optimal use of your um, capacity, processing capacity, of your compute. But if it's a real-time application, then batching may not work, because in batching, you may delay processing of some inputs so that I can gather the batch, assuming they all don't come at the same time. But for a real-time application, you just have to handle the requests as they come, and so you have to stream. It's really about what is your use case, right? Now, batching or streaming doesn't stop retries and fallbacks. You can apply retries and fallbacks whether you're using batch processing or you're using stream processing. They are not mutually exclusive. Was that answer your question?
Oh yes, but I guess that we may determine, especially for the batch or batching, maybe that may determine the timing of retries. I don't know. I'm just
No,
thinking randomly,
no,
sir.
it
I'm
doesn't
not.
determine the timing of retries. You have already gathered the batch you want to process. You've tried processing it and you encounter a failure. All the try is doing is implement some backoff, and on the expiry of the wait time, retry that same process that failed. So if it's a batch processing of a particular batch that failed, once the wait time expires, we try processing that same batch, that exact same batch again. If it still fails, and based on your retry settings, if your retry settings allow you to retry once more, you still retry again after your wait time expires again. So retry time is not the time you're waiting for to assemble the batch. No. For you to retry, you already have the batch, you've already tried processing that batch, and then that attempt to process it failed. So you already have the batch. The essence of the waiting, the backoff is, if you keep retrying immediately, you might make the issue worse, particularly if the resource that you're trying to use is a shared resource. There could be multiple people trying to use that same resource at the same time. And maybe that's why you even had the failure in the first place. So just imagine every of those people that are trying to use that service, you try immediately. It means that it will keep failing forever. Backup algorithm is you wait a little, give chance, you give some chance for the system to stabilize before you retry. And typically, for shared systems, your wait time should actually be random. Yes, exponential, but also random. Because if it's fixed, then most likely all the systems will also retry at the same time. So it should be randomized to minimize the likelihood. Well, that's assuming that if the failure is because of collision, as in more than one request coming in at the same time, then you apply randomized back off. But if that's not the case, if it's just about a transient system instability, then you may not randomize. But randomize is actually helpful in many cases. I mean, randomizing your wait time when implementing a back-off process. Does that answer your question, Olawale?
Absolutely, sir. Thank you very much.
Okay. So does anyone else have a question or comment on what we've talked about so far today? We move ahead. Okay, so we move on. Now, we talk about LangChain callbacks. Callbacks are actually LangChain's inbuilt way for implementing. It's the basis of implementing observability. So it provides a lens into the behavior of I had mentioned that earlier, into the behavior of the LLM or agent or chain, as the case may be. So callbacks they are a standardized hook mechanism. There are different hooks that you can use for callbacks. So depending on the hook, when a specific event happens, the handler for that event performs some action that you have predefined based on your exact implementation. Callbacks allow observation into the LangChain application's execution. They also allow interaction with the execution of the LangChain application. So via callbacks, you can observe the application execution. You can also interact with the application execution. It's important to note that callbacks do not modify the core logic of the LangChain application. No, they do not modify the core logic of the application. The application still proceeds, still executes as normal. The callback just allows you to hook into the execution loop for that application. They are implemented through callback handlers, and a callback handler has to implement the base callback handler interface. And how you integrate these callback handlers into your application is via the config arguments in invoke, invoke, or stream method calls for LangChain runnables. So like your LLM, we've been using invoke method so far, right? We could also call those our LLM or chain with a invoke. That's asynchronous invoke. So if you are building an asynchronous application, a sync application, then you should use a invoke. Or stream if you want to stream the model output instead of returning the complete output for a given input. You could stream the tokens of the output, one token at a time. If that's what you intend to, then you should use stream. I think there's also a stream if you want to a synchronous stream, I think. But don't put me on that for long. But I think there is a stream. But right now I'm sure of invoke, and stream. I think there's a stream. Anyway. So here are the some key callback event hooks. There's on-chain start and on-chain end. On-chain start and on-chain end, it typically executes at when a chain starts at the beginning of the chain, when execution of a chain starts, the very beginning and the very end. But we need to bear in mind that the way LangChain applies this, when you associate the chain with the LLM chain constructor, is different from the way it's applied when you compose the chain with the LCell, LangChain expression language. But there's still a way around that anyway. Then there is this on-chain start and on-chain end tracks the overall execution flow of the chain, and you can also use it to track the execution time for that chain. Assuming you capture the time when on-chain start runs, and you also capture the time when on-chain end runs. The difference between those two time instants gives you the execution duration for that chain. There's also on LLM start and on LLM end, which would execute at the beginning of the LLM's execution for LLM start, and then on LLM end will execute at the end of that LLM's execution. So you can use this to capture the prompts to the LLM, the token usage of that LLM, and the model latency. For latency in this case, it's about for when you run on LLM start, you capture the time. Then when you run on LLM and you capture the time, and then you find the difference between those two. That difference is the latency of the model. There's on-tool start and on-tool end, which relates to tool. On-tool start runs when that tool is called, and on-tool end runs when the tool gives out its output. So that's when the tool execution ends. There's on LLM error and on tool error. These are called when there's an error in either the LLM or the tool, or an LLM or a tool, as the case may be. They capture exceptions and stack traces for immediate debugging. Is there any question on this so far? Any question on anything, any of the stuff we've talked about today? Or comment?
Okay, since you said we can talk on something apart from today, sir.
No, what we've done today.
Okay, all right.
Or if it's something that we've done in the past that relates to what we've done today, fine, you can talk about that if it will help make what we are talking about today clearer. But if it's not directly related, we can leave that for some
not
other
directly
time.
related. Yeah,
Okay,
not
so
directly
let's leave that for now. Let's not get off track. Okay, so I guess we'll continue. Now, logging and tracing. You can use you can implement use a basic callback for logging. For example, using the standard output callback handler. And when you are instantiating an LLM model, for example, like Chat Olama or Chat Grok or Chat OpenAI, whichever, if you set verbose equals true, you are essentially hooking into the standard out callback handler. And so the LLM is going to be verbose, it's going to provide more text output, which gives you more insight into what is happening within your chain or your LLM, as the case may be. Alternatively, you could use a handler directly. So how you implement a handler, it depends on you. But typically, you would define a custom callback handler, and within that custom callback handler class, of course, your custom callback handler has to implement the base callback handler interface. That's what makes it function as a callback handler. So you define your custom callback handler, and you implement or you override the specific hooks that are relevant to your application. And so whatever code you provide for each of those hooks is what will be executed when that hook is triggered. So basic callback shows could be used to show the third action observation loop in real time, assuming you're for some, say for a React agent that allows you to have more insight into the internal workings of that agent as it executes. Then for production logging, you should typically use a more robust implementation, like create a custom callback handler to send events to a structured logging system like CloudWatch by AWS, Google, or Google Cloud Logging, or Datadog. And I mean, these are frameworks and platforms and so on that are built for observability, tracing, and insights. And so you could use a custom callback handler to capture events as your application executes, and then you send those events to the specific production logging. What's the term I will use? Your production logging setup. Let me use that term. So this will focus on logging structured data. For example, event name, run ID, tokens used, latency, and so on. You structure it, you send it to whatever of the only platform that you are using for your application. Any questions so far? Any comments? Okay, none. So we move ahead. Now, at this point, we are going to do some demonstration of using custom callback handlers for logging, for observability. I have already sent some code to the Discord channel, so I would advise that at this point you copy that code into your IDE, and so you can fire it. I will run it. Let's see how these callback handlers look like and how they work. Let's have some hands-on on this. So I'll temporarily stop sharing my screen, and then I'll open my own IDE where I have the code. And I think I'll stop recording a bit. It also gives you time to fire up your own IDEs, copy the code from Discord, and we're also ready to execute on your own end. So I'll give just a few minutes for you to also pull the code from Discord. Okay. So here we have sample code for demonstrating logging using callbacks. Firstly, well, we first configure login. We are going to use the login module. We'll demonstrate using it, and we'll also demonstrate printing out whatever we want to capture. Of course, you could log into a file, but even when we're logging, we are sending our logs to the standard output, which in this case is the stream. You could log to a file, you could send to some observability platform like Cloud Login, or so on and so on, or Datadog. So we define after configuring logging, we define a custom callback handler, a class custom callback handler, which inherits the base callback handler, essentially implementing that interface. And for this, we're going to use this callback handler for the LLM. And we implement the on LLM start, on LLM end, and on LLM new token hooks. We also define a class, custom chain login handler. We are going to use this handler as a callback for the chain itself, not just the LLM. I'll come back to the specific logic for each of these handlers. And here, we define the on-chain start and on-chain end hooks. Next, we define the LLM. Here we use Chat-O-Llama. And we attach the callback handler to it using the callbacks argument, which takes a list of callback objects. So you could have multiple callback objects attached to a specific runnable. Then we build a chain. We define a prompt template that just asks what is this capsule of, well, a given country. And we compose a chain based on comprising that prompt template and the LLM to which we attached, to which we bound custom LLM callback, custom LLM callback handler. Now, there are two approaches for attaching a callback handler to the chain. One is with using the with config method of LangChain runnables. And in this, when we are using that, we provide the callback handler in as the value for the callbacks argument. It's still a list, just like we had when instantiating the LLM. That's one. Don't worry about this run name. We'll get to that. Another approach, an alternative will be to attach that callback handler at the point of execution. Now, when we use the with config method, the callback handler is baked into the chain. It becomes part of that chain. Anytime you use that chain, that callback handler will be triggered, assuming the events, it will be triggered. Any of the hooks will be called, assuming the corresponding event occurs. But when you apply the config at runtime, like I did here, even though I commented it out here, but we'll try both approaches for this same chain, and we'll see that the results are the same. But there are two approaches. The only difference is, in this case, you're baking the callback handler into the chain, in this case, you are attaching the callback handler at the point of execution, meaning that for different executions, you can use different callback handlers. Whatever callback handler, whatever running, whatever config you pass here becomes the config. Of course, the config contains the callback handler. You define the callback handler within the config object. In this case, we are using a dictionary. Instead of a runnable config object, you could also use a dictionary that can be converted into a runnable config object by LangChain. In this case, we are using the simpler approach of using a dictionary, which LangChain will convert to a runnable config and attach it to this chain at runtime. Now let's look at the components of this code in detail. For the custom LLM callback handler, on LLM start, we are simply just printing LLM starting with prompts. Now, if you look at the inputs to this method, we have serialized, which is a dictionary of a string, mapping a string to any. This serialized actually represents any serialized objects, an example of which is an LLM. It's a mapping between, it represents the LLM in this case anyway, since it's on LLM start. And then we have the prompts, which is the list of prompts that is passed to that LLM, and then any keyword arguments that are also passed. And all it does is to print out LLM starting with prompts. It adds the prompts. For on LLM end, the only inputs it takes are the response, which is the output of that LLM, and any keyword arguments. And in this case, our logic is that it prints out LLM ended with response, and it extracts the generations, the text from the response text from that LLM response. And therefore, LLM.new token, essentially it streams, this is triggered for each token that is streamed from the LLM. So essentially, this streams the output from triggers the hook for each token generated by that LLM, and all it does is say new LLM token. It echoes that token and goes to a new line. Well, you can use whatever end value you want, any stream there, and it flushes. We have flush all through. For the custom chain login handler, the custom handler we have for the chain, we have to apply a logic to overcome the challenge of how LangChain applies custom handlers to chains. If we use similar logic to what we use for the LLM callback handler, we'll find that for each component in that chain, this handler will be triggered. And so, yes, in this case, it still gets triggered, but we don't get outputs we don't get to capture the specific information we want, except certain conditions are met. And what are those conditions? We only want this to be triggered. We only want to capture, we only want these hooks to capture the, only want the logic, how do I say this now? We only want to log the desired information when the overall chain starts and when the overall chain ends. And so we define this value called target run name, and we assign the value of chain name to it. If you look at the beginning, we specify chain name to be callback chain. And then we also specify target run ID. For on-chain starts, what we do is that if the keyword arguments contains that chain name that we specified, we know that it is the chain itself. And when we define the chain, we attach that name to it, and that's why we have the run name in the config. This run name that we set to chain name is saying that, hey, chain, your name is callback chain. I think that's the value for chain name. So when this hook is triggered in the keyword arguments dictionary, we will have a key called name, and the value will be whatever we have set as run name. Hence, for the fact that we've specified the run name argument when defining the chain, when this onChain start hook is triggered, there will be a key called name with a value of that chain name in the keyword arguments. And so we say, once we verify that the components, in this case, the serialized, that will be the component. But we want to verify the component is the chain itself, and we can verify that by confirming that the value for the name key is target name. Then we set the value of target run ID to the run ID in that keyword, in the keyword args dictionary. This target run ID helps us to capture when the chain ends, because remember that the inputs to onChain end does not include a serialized, and so we don't have any name key in these keyword arguments, but we still have an ID, and that ID we have it as run ID. So once we set the target run ID, it enables us to be able to determine when the chain itself ends, so that we don't trigger the onChain end, say when the prompt template ends. Without this, you see that onChain end will trigger when the prompt template ends. Well, it would also have triggered when the LLM ends, except that now we have a specific callback handler for the LLM. And so when it's onChain end, we check for the run ID. If the run ID matches that run ID that we have captured earlier, that specifies the chain, we now know that it's the chain that ended, and we also log the corresponding information. I think that's basically the details here. And what we're asking the LLM is, what is the capital of France, since we are providing France as the value for country. So at this point, I'll try to execute this and we'll see what the output will be. Note that for this run, we are using the method of attaching the callback to the chain using the with config method. Just a moment. Zoom is intercepting I need to pause a bit, and then I need to stop sharing a bit and then come back. Okay. Okay. So we can execute now. Now, if we use a print statement for custom chain logging handler, the outputs we have will be in the right sequence. Notice that in our actual chain, we should have this info callback chain starting with inputs country France, which is what the on-chain start hook is supposed to give. It should come first before the LLM start hook. But because we are using login, it's a bit slower than printing directly. And that's why you see it coming after. I would like you to try the variation where for custom chain login handler, on chain start, instead of using login.info, use print. And for the on chain end, instead of using login.info, use print. Compare the outputs with the output when you use login.info. In this case, you're seeing that even though LLM starting with prompts, that's the on LLM start hook was actually triggered after the on-chain start hook, the output of on LLM start hook is coming is getting to the screen first before the output of on-chain start hook, because the login itself, calling login provides a bit of extra latency. But anyway, we'll still capture what we want. So for the on LLM start, it prints LLM started with prompts, gives you the prompt. What is the capital of France? A human message. And then we see the first log from custom chain login handler, info. Yeah, login.info. Callback chain starting with inputs, country France, which is what we should have here. The target run name is callback chain. That chain name was specified earlier, starting with inputs, the inputs. Then we have info.request. Now, we did not specify this, but login, the login method, the login module captures that detail. So the HTTP post request to OLAMA, it captures it. If you use print for instead of login.info, you won't capture this part. So you see that by using logging, the login module along with callback, we are getting more insight into what is happening in this chain. There's a message chat. Okay. And then the next thing we see is what we get from on LLM stream, on LLM new token. Actually, it streams the tokens. The capital of France is Paris, and so on and so forth. And you see that the full output is what we get with on LLM end, where we have this. The capital of France is Paris. It's a very common and straightforward answer. Do you want to know more about Paris? But for the on new token, it provides each token separately on a new line. And then final result, which is what we have as the actual output of the chain here. And then it still logs the on chain end hook is called and logs this. Yes, we could have specified in our configuration of our logging configuration that the logs be written to a file or be sent to maybe Datadog. If that were the case, we won't see this login information on the screen. That is one run. The second run I want to do here is, instead of using chain with config, here I'll use chain itself. So it's not the chain that we had attached the callback to. and we'll dynamically attach the callback using the config argument when config argument of the invoke method. And so we'll still run this, and you'll see that it gives you exactly the same outputs as the other method. I think we had, okay, no. Now, when we attached the callback dynamically using the config argument, you see that the sequencing is well, a bit better, even though for the LLM to have given you the output, the HTTP post would have happened first before you get. Okay, no, it's correct. This is when it starts and then it calls this. But then the first token of the output is displayed before the log of the HTTP post. So that means there's still a bit of sequencing issue, but then that's because of the latency we get for using from using the login module. So here is essentially the same output, apart from the difference in the sequencing of the outputs from the different callback hooks. And that's essentially what I have for you today. Like I said, please try to play around with this code, which is the same thing I say for each code we use to demonstrate in class. Try to play around with it, try different combinations, attaching the callback dynamically at runtime, attaching it when using the with config method, where we had baked it into the chain, using prints for the chain custom chain login handler hooks instead of login.info. Try different combinations of these and see what outputs the code gives you. And that also helps you get a better hang of this. And essentially, we keep building on what we learn at each point. That's basically it, ladies and gentlemen. Does anybody have any question or comments?
Sir, tonight, gas bill.
Hi.
Sir, I'm just following today's zone in the spirit, sir.
Okay. Here's what I would advise. I understand that feeling. You really need to get into playing around with this code. Yes, it's something entirely new. We're talking about callback handlers. We're talking about hooks, right? But if you have followed everything we have done up to the point of building chains, the only thing we did today was we defined callback handlers. Of course, we use login, but login is something you should know. But even without login, we can use print statements. So let's leave login first. All we did was define callback handlers with hooks, and we attach the callback handler to the LLM or the chain, as the case may be. For the LLM, we attach using with callbacks, just like we did when we were, I think that was when we were attacking fallbacks. There's a with fallback method. When we are trying to implement retries, we use with retry. In this case, we are using with callback. I want to see where the LLM. Okay, for the LLM, we just apply callbacks to it. But we can also use the with callback since the LLM is still a runnable, right? For the chain, we use with config. No, it's not with callback. It's with config that we can use, not with callback. Sorry about that. But we use the callback parameters of the LLM. For the chain, we can either use the with config method, or at runtime, we can attach it dynamically. We can also do this with just the LLM, assuming it weren't a chain, assuming it was just an LLM that we're invoking. So the invoke method has a config. It's actually good for you to get familiar with this config argument of the invoke, invoke, and stream methods, because when we get to full defining to creating full agents, we'll use this config argument quite a bit. It allows us to pass a lot of parameters into the agent, which it uses when it's running. So what I would advise is play around with this code. Try different variations to it, different permutations of the different varieties. And by the time you do this, you break it, you fix it, you get familiar with it, and it will not be somehow again. New material could sometimes be like this, but there's really nothing much here. All you need is to play around with it, and that demystifies it, and you see that it's just code. Well, I still have one more thing I should talk with, and I think I should talk about rather. And I think I need to share my slide for that, but that's not much. It's just information that you should be aware of. Not much detail about that. So let me share my slide again and talk about that. Okay, so for advanced observability, LangChain has a dedicated observability platform called Langsmith. Langsmith is built on the callback system. So it uses callbacks. Langsmith, it facilitates. With Langsmith, you can see a visual hierarchy of each component call. So you have a complex chain, or you have an agent that's for each run, you can visualize the hierarchy of each component call. What components connects to which one, and so on. So you can see it in a hierarchy. You can inspect immediately, you can inspect each prompt, each response, and the intermediate variables at each step. You can inspect the prompt, the response, and intermediate variables at each step of the chain's execution or the run, as the case may be. So it provides, it makes it easy for you to have deep insight, deep observability into the components and the execution of your agent or your chain, as the case may be, which facilitates debugging and tracing. Now, in our basic example that we had, as we had implemented on LLM error or on chain error, that will also capture when you have error issues. Just imagine, if you remember, I mentioned that the best practice for resident application is you implement retries. So for transient failures, retries handle that. If your retries after the maximum retries based on your configuration, they are still a failure, you go to a fallback. If all your fallback components still fail, then I mentioned that you raise an error. One way you can, and I think that was one question that I think somebody asked a question about that, raising that error. You could use a callback to trigger that error when eventually the final failure happens. A hook can be triggered to expose that error, to raise that exception. And of course, if you attach a service like Langsmith to your agent, you have deep insight into it. You can trace end-to-end runs. You can debug. It makes debugging easy. In our case, if in the code that demonstration code, if I had implemented on LLM error or on chain error and say we logged it to file, whenever you have bugs, you can look at those logs, which logs are very useful for debugging. Now, use cases, agentic use cases for Langsmith include root cause analysis. Assuming there's a failure, assuming you have a failure in your application with Langsmith, excuse me, sorry for that interruption. So I was saying that the use cases in agentic AI, the use cases of Langsmith include root cause analysis. And I was explaining that as when you have a failure or you have some unexpected behavior in your agent, with the deep observability provided by Langsmith, you are better able to identify which component exactly caused that failure or that unexpected behavior, the root cause of that unexpected behavior. Another use case is prompt engineering, where you can compare two prompts side by side. And because of the visual hierarchy that Langsmith provides, you can see the run through your agent for each prompt. And that way you'll be able to determine which prompt is better or overall and which one is better at different points, allowing you to better tune your prompts for your use case. And then also regression testing, where it helps you to ensure that any modification you make to your agents does not lead to failure of previously successful runs. Of course, well, not of course, just to let you know that Langsmith is not free. You have to pay to use Langsmith. But there are open source alternatives, including Langfuse, Helicon, Arise Phoenix, and Open LLM-etry. These are some open source alternatives to Langsmith. But Langsmith itself is tightly coupled to LangChain. So it makes it easy to use Langsmith with LangChain, but you have to pay to use Langsmith. So it's a trade-off. Use Langsmith, it's easy to use, but you pay, or use an open source alternative like Langfuse or Helicon, but you need to take a bit more action to set it up, to run it. And that's basically what I have for you for today. So does anybody have any question or something that we can clear now, depending when you watch the video later? I'll have, okay, David, go ahead.
Okay, thank you, sir. I just wanted to ask, the way your console displayed the results more like in a list, vertical order. I don't know if it's something that is peculiar to PyCharm or it's also something I can do to get same.
How does yours display it, and what ID do you use? Could you share your screen?
Yes, sir.
Okay, so let me stop sharing mine.
Okay. Can you see my screen, sir? So you're muted. If
Sorry, I just realized that I see your screen. Try to run the code. Let's see.
okay,
Okay.
this is the result I'm getting on my console. So it's more like in the horizontal. Yeah. So it starts from here, over change starting input, control brands.
It's not horizontal. It's still the same way mine is. Callback chain starting with inputs this. LLM starting with prompts this. Info. Yes. This is the HTTP post. LLM ended with response. Callback chain finished with response. Let's see what your it's essentially the same thing, is it not?
Yes, sir, it's the same thing, but like yours is kind of in a list, like just straight down, not like after comma this, after comma this. No, it's just like a list, a vertical order. But this one shows, even though it stays this vertical, but from this part, this total tokens like this should come under this prompt tokens.
But remember that you're using a different model from mine. You're using a different provider. You're using ChatGrok. You're
Yes,
using
sir.
Grok. I'm using Olama.
Yes, sir. I changed it actually because I think I'm even more convenient. This one is even more convenient to use than Olama.
Now, I don't have any issue. My point is that it may be because that difference, the difference here is just in the output from the LLM, is it not?
Yes, sir.
It may be because you're using Grok. What I will do is probably tomorrow or so, I'll run the same code with Grok and see if there's a difference, then we'll know that that's why. I can't really look at this in detail now because it's a bit small. I'm just on a small laptop screen.
Okay, so no problem.
So I'm going to run it with Grok, and if it's the same thing with what you have here, we know that that's why. But the only thing that's different here is the LLM output.
Yes, sir.
Um, can I see your what's the name on LLM end hook?
This is it now.
No, the hook in the callback handler on LLM end in the callback handler.
Bring this down.
On LLM end. Okay, I think it's just because I think it's probably because you use Grok. Let me even look at mine again. I think it is because you use I think the difference is
Okay.
just a moment. I'm gonna okay. Result. It's the same thing. It's the same thing. Let me look at yours to just confirm finally. Can I see that the output again? The output on your terminal. It's the same thing. I'm going to open mine again. I'm going to share. Just stop sharing. Let me share. Okay, let me even stop recording because we don't really need to record this.